Okay, so one more rule left. Actually, this is not a new rule, but a new form of an existing rule, namely the power rule. So this is rule 7. And it's like this. If n is a negative integer and x is non-zero, then x to the power n is differentiable with respect to x, and the derivative of x to the power n with respect to x, it's just like the one with positive exponent. I mean, the power rule that we have already seen, the form of the derivative is just like that. That means n times x to the power n minus 1. The only difference now is that n is negative. So let's see how we can prove this. In the proof, we will use the quotient rule of differentiation. Since n is a negative integer, so n is equal to minus n, where m is a positive integer. Obviously, because every negative integer is the negative of some positive integer. For example, minus 2 is the negative of 2 and 2 is a positive integer. Since x is not equal to 0, it follows from the quotient rule for derivatives that this exists. Why? Well, because we can now express this nth power of x in terms of the mth power of x using algebra. And when we write that expression, that will appear as a quotient. And that, of course, is this. Actually, there is one more step. If you want, you can replace n with minus n. The next to the power minus m is this. So now by the quotient rule, and note that you are able to apply the quotient rule because x is non-zero, and so x to the power m is also non-zero. So what was the quotient rule? You have to take the square of the denominator. And then in the numerator, first you keep the denominator, you don't do anything to it, and differentiate the numerator minus. Then you keep the numerator intact and differentiate the denominator. So you can see that because 1 is constant, so by the constant rule, This is actually, this is 0, so 0 times x to the power m is 0. Minus, there's of course no need to write 1. Now this is where you can use your usual power rule. Why? Because m is a positive integer. So the derivative will be m times x to the power m minus 1, and the denominator is x to the power 2m. So now if you manipulate these powers, it will be m minus 1 minus 2m minus m times x to the power m minus 2m is minus m, and minus 1 of course will just be minus 1. Now recall that minus m is just n. So you get this, and that was the claim. So not only is x to the power n differentiable even when n is negative, but you must consider this additional condition as well. X needs to be non-zero, because otherwise you will be dividing by 0, which is meaningless. Not only is it differentiable, but the derivative appears in exactly the same form that we have for positive exponent. Okay, so that's the proof. Now next we have an example illustrating this. This is example 10. So if you differentiate, when you are thinking of negative powers of x, what that means, when we say negative powers of x, we do not mean minus x to the power something, no. We mean a power of x where the exponent, the number which appears above x, is a negative number. The first negative number is minus 1. So if the exponent is minus 1, then it's just 1 over x. So now you see that previously what would you have done? In this case, you had to use the quotient rule to calculate this derivative if x is non-zero. Now, however, because you have this version of the power, you can also call it a power rule where the exponent is negative. Because of this version, you can now straight away use the formula. So it will be minus x to the power minus 2. So which is this. Oh, sorry, there will be a minus sign. Minus 1 over x square. And of course, it's understood that here x is non-zero. We are not just mentioning that. Similarly, the derivative of 1 over x square is minus 2 times x to the power minus 3, because minus 2 minus 1. So that same form we have here also, even when the exponent is negative. To remember it, you recall how we remembered the form of the derivative. We just bring the exponent down. So if it is minus 2, you bring it down and you multiply whatever you are going to write here by minus 2. And then you subtract 1 from the exponent. This time, since the exponent is minus 2, so minus 2 minus 1 becomes minus 3. So that's how you have these derivatives. Next, see example 11. Find an equation for the tangent to the curve So what is the curve? Y equal to x plus 2 over x. At the point 1 comma 3. So it's understandable why this function has been chosen. Curve means it's a function, so the curve is the geometric representation of the function because we have 2 over x. We have dy dx. Ideally we should write we are given the curve this and then we write differentiating this with respect to x. You can write those things, okay, but we are getting to the main thing straight away. So by the sum rule, first you will differentiate this x, and differentiating x gives you 1. You go back to the power rule and see why this is 1, and then you have to use the constant multiple rule. By that rule, you write 2 outside and then you differentiate 1 over x, which gives you minus 1 over x square. So we know what this means geometrically. Geometrically, this is the slope of the tangent to the given curve at the point whose x coordinate is x and y coordinate is x plus 2 over x. So from this we can write, so the slope of the tangent to the given curve at what is the point 1 comma 3 is dy dx evaluated at x equal to 1. So if you replace x with 1, what will you get? 1 minus 2, because this will become 1 and there is a minus sign. 1 minus 2 is minus 1. So now you have to write an equation for that straight line which has slope minus 1 and it passes through this point. So that's a simple matter. Hence, an equation for the tangent to the given curve, without writing given curve every time. If you want, you can write this also. At the point is, so you write the point slope form of the straight line. Y minus 3 is equal to slope times x minus 1. So you can do some things to this. Say you add 3 to both sides, then the left hand side will be y, and the right hand side already is 1 minus x. So adding 3 to 1 gives you 4, so it becomes 4 minus x. Okay, so that is the tangent to this curve at the point 1, 3. Alright, now sometimes what happens is that there is no, you now know quite a few rules using which you can really differentiate many functions, especially polynomial functions and rational functions. Using the various rules we have seen so far, you can differentiate such functions. But sometimes it becomes slightly confusing as to which rules we should use because there are options. Now let's see that it's not always, what you can say, you should not look at the form of a function and straight away decide which rule you should use. Sometimes you should take some time to think of it, and then you will see that doing a little algebra and changing the given form of the function sometimes simplifies things. This next example illustrates that fact. Actually, it comes under a heading, choosing which rules to use. Okay, so example 12. Say you are given this function. Y equal to x minus 1 times x square minus 2x divided by x to the power 4. Looking at the form of this function, it seems like we should naturally use the quotient rule. Oh, and one more thing, x is non-zero here, that's understood. But if you use the quotient rule, and then you may also want to use the product rule because the numerator is a product of two polynomials, it may become somewhat long. Instead, we can do something else. We can do a little algebra to make this simple first. We can simplify this first, and then we will see that our job it becomes much easier. Like this. So what we can do, let's do the multiplication first in the numerator. So x cube minus 2x square, this times this, plus this times this, and then the negative, because we are then multiplying by minus 1, plus 2x. So this gives us a cubic polynomial in the numerator, minus 3x square plus 2x. But now you can do division also. This is not always the case, but at least in this case you can do division because the denominator is simply a power of x. So this is going to be x, of course, you understand that x cube divided by x to the power 4, minus 3 times x square divided by x to the power 4, plus 2 times x divided by x to the power 4. That's what I mean when I say you can divide. And after you simplify further, you get this, minus 3 times 2 minus 4 is minus 2, plus 2 times 1 minus 4 is minus 3. So now you see that it's simply a matter of using the sum rule, the constant multiple rule, and the power rule with negative exponent. Only these things have to be used, and the use is very simple. So now if we differentiate this y, we don't have to deal with those long expressions that may result from using quotient rule, product rule, those things. So it's helpful to first think for some time which rule to use, and then only you go for solving the problem. That may save time. So dy dx, of course, this when you differentiate, it will be, let's write the form, okay. It will be this. Minus 3 times, when you differentiate this, it will be minus 2 times x to the power minus 2 minus 1 plus 2 times minus 3 times x to the power minus 3 minus 1. Ideally, if you are being asked to really show the uses of all these rules, then you should do, you should not straight away write like this. You should apply the rules, one rule in each step. Maybe you can apply 2 rules in one step, but if you do, you mention which rules you have used alongside that step. And that's why you should not solve the problem like this. You should solve it centrally. That means you write one line here, after that you write the next line, and then the next line below that, so that you have some space on the right hand side where you can write the uses of the rules. But eventually, when you really are going to differentiate things, especially you will use, or you have already used differentiation a lot when doing physics. There, of course, you need not write anything, and you have to learn sooner or later to really do things fast. So that's why I am doing like this. Minus x to the power minus 2. Minus 3 times minus 2 is plus 6. X to the power minus 3. 2 times minus 3 is minus 6. X to the power minus 4. Now if you want, you can write this as 1 over x to the power 4. Then take LCM and do all those things to ultimately express this answer in some form like this. If you want, you can do, or you can keep it just like that. Okay, so this is your differentiation. Now the next thing is second and higher order derivatives. Alright, so we now know, we know very well what derivative means, what its geometric meaning is, and it can also be interpreted as rate of change. But besides these things, of course, you can actually continue differentiating. Suppose y is a differentiable function of x, then the derivative of y with respect to x, which we have discussed for so long, also has another name. It's called the first derivative or first order derivative. Then y prime, it's the prime notation, or you can use this notation also, is called the first order derivative of y with respect to x. Now it may turn out that this y prime is also a differentiable function of x. If y prime is also a differentiable function of x, then we can differentiate it again with respect to x and write that quantity as y double prime. That means prime of y prime. Or this is what it actually is, the derivative of y prime with respect to x. Or if you write what y prime is, that is y prime itself is a derivative, then you get this. Where this should not be interpreted as product, this is not multiplication. Since differentiation is an operation that we apply on y, it's a function actually. You apply this function on y to get another function, y prime. So this is another application of that same function. It's like this. See, we already have learned about function composition. When you have two functions, you can compose them together. For example, if f is a function and g is another function, then you can compose them, f composition g. What does it mean? It means that first you apply g on the input x, and whatever you are getting as output, on that you then apply f. If the situation is correct, this of course cannot always be talked about. You know when it's possible to talk about composition of two functions. Simply put, it is possible only when all the g outputs are in the domain of f, because then only f of that will make sense. If the situation is correct, you can apply the same function two times. Say g is equal to f. Differentiation, however, is a special type of function where the inputs are not numbers. The inputs themselves are functions and the outputs are also functions. For example, when we say that this is 2x, what we mean is that differentiation is a function in which we have taken this input fx equal to x square. That function itself is the input. And what does differentiation give us? It gives us another function as output, which is gx equal to 2x. In that sense, you have to see this. This is actually composition. Applying the differentiation function two times on y successively. And if you do this, there is a notation for this. To indicate that we have done it two times, we write like this. We write the 2 above d, and here we write the 2 above x. And this is read as d squared y d x squared. If you really want to read this properly, that's how you have to say it. D squared y dx squared, not d squared y divided by dx squared. We have already talked about this, that this is not division. This also we read as dy dx, like that, d squared y dx squared. And when we consider this is called the second derivative. Let me, because this is not complete, the sentence continues. So let me use brackets. This thing is called the second or second order derivative of y with respect to x. If this also turns out to be a differentiable function of x, because this is again after all a function, then you can continue differentiation and consider the next derivative, the third derivative or third order derivative, which of course will be this y triple prime and this will be denoted like this. And if it continues like this, you do not keep on going writing prime, prime, prime. You write like this. You don't simply write 4 as a superscript, but enclose it within brackets, means parentheses, to indicate that this is not exponent. This is not exponent of y, but we have differentiated y 4 times with respect to x. And another notation for this same thing, of course, is going to be this. The fourth derivative of x, or of y, or fourth order derivative of y with respect to x, if it is differentiable that many times. In general, if n is any positive integer, then this is the nth derivative or nth order derivative of y with respect to x. And the other notation is this. And this, the meaning of this is, of course, this. I said that when n is a positive integer, then the nth derivative of y with respect to x is the derivative of the n minus 1th derivative of y with respect to x. However, what happens when n is 1? In that case, you get this. This, however, is our ordinary first derivative. But what is this? We haven't actually said anything about this. Well, this is simply the function itself, which just means that this is the zeroth derivative, means we haven't actually differentiated. We have the original function itself. Okay. So with this understanding, and these are the higher derivatives. The first derivative is the one we have been discussing so far, and these are the next higher order derivatives. So they also appear quite often, and you already know how they appear in classical mechanics. For example, if you have something which is moving, okay, it's changing position in time, then you can calculate how far it goes in what interval of time, and you can differentiate that distance by time to get speed. If you differentiate this once more, you get the magnitude of acceleration. And that's how, with this quantity, you have your Newton's second law and other things. Okay. So you already know these things from application. But one can differentiate even the acceleration with respect to time to see, for example, how acceleration is changing. This happens when the force itself is changing. For example, you are sitting in car, right? And usually what happens is that there are, the road, of course, is not a theoretical straight road. There are bends. The road condition may be very bad. So at any moment of time, you have some different force acting on you. So you are pushed a little on this side, on that side, and that creates motion sickness. And that is change in acceleration. So the rate of change in acceleration is the next derivative of acceleration. That has a name also, it's called jerk. So we will talk about this other things. But let's now end our discussion by calculating the successive higher order derivatives of this polynomial in the last example of this section. These things arose in applications first, and then their theories were developed. Say our function is now this cubic polynomial, x cube minus 3x square plus 2. So if you differentiate once using all the rules that you have learned so far, so you will be using the constant multiple rule, sum rule, power rule. First you will get 3x square from this term, then minus 3 times from x square you are going to get 2x plus 0. So this becomes 3x square minus 6x. And note that any time we differentiate a polynomial, we get another polynomial of degree 1 less than the previous one. This is a cubic polynomial. This is a quadratic polynomial. And because polynomial functions are always differentiable, so in this case at least you can keep on differentiating as long as you want. So let's see how far we can go. The second derivative will be obtained by differentiating this. Minus 6 times differentiating x, we get 1. So differentiating a quadratic polynomial has given us a linear polynomial. Now we can differentiate once more with respect to x. and that will give us 6 times 1 minus 0. So we have reached a constant polynomial, but that is also differentiable. That, however, gives us 0 by the constant rule. 0 is also differentiable, it's a constant function, and the successive higher derivatives just continue to be 0. You don't get anything new. You can go as long as you want, but you keep on getting 0. And do you see one more thing, that no matter how large the degree of the polynomial is and what the polynomial is, regardless of all these things, if you keep on differentiating sufficient number of times, you will eventually reach 0, and after that the successive derivatives will continue to be 0 without any end. Okay, so this is where the section ends, and after this we have exercises. So we will do those things, and tomorrow we have linear algebra, and we have started Jordan canonical form. I think we did only a little lemma or something. So tomorrow we will see what comes next. So that's just it for tonight. So see you tomorrow with linear algebra. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.